Okay, good afternoon. Welcome to the last session of TechEd. I know you're all probably exhausted by now. You've had 3 days of PowerPoint presentation, 3 days of heavy code, and you're all going to be mentally exhausted looking for something nice and relaxing. That's why you've come to a 400 level session. So this is a 400 level session. We are going to go fairly fast, we're going to go fairly deep, and there's probably going to be things that maybe I don't explain well enough. So if there's something that leaves you a bit baffled, please do raise your hand, stop me, ask me to explain again, ask me to give another example. If you don't understand it, there's a good chance that half the other people in the room don't understand it as well. They'll be really grateful that you asked the question. Go for it. Okay, so what do I want to cover this afternoon? We're going to look at dynamic and metaprogramming in .NET, and just going to cover a bit of a grab bag of topics within that. Firstly, we're just going to have a quick review of what the C# dynamic keyword actually does, what it means. I'm guessing that most of you are pretty familiar with that already. Then we're going to look at how we can write objects that respond to dynamic method calls. We're going to introduce a class called Dynamic Object, which is part of the .NET framework, and see how we can use that to create a more dynamic style of programming, to offer our clients a more dynamic style of programming. We're going to look at a couple of techniques for generating code at runtime, why you might want to do so, how you might do so. Then we'll take a look at we'll take a look at how you can use the same capabilities without involving the dynamic object, looking at the raw interfaces that underlie that. And then we'll take a little bit of a dive into how C# dynamic actually works on the inside. If we have time, there's some topics I'm interested in talking about that go a little bit beyond C# dynamic, but we'll see how we're doing for time. Okay, so I think we've seen enough PowerPoint in the last 2.5 days, so let's switch over to Visual Studio and get underway. Okay, so I want to just kick off with a quick refresher on the dynamic keyword. This was introduced in C# version 4. And what it basically does is it says to the compiler, hey compiler, I'm smarter than you are. Compilers are dumb. They are very untrusting. A compiler will only let through something, or the C# compiler will only let through something that it can prove is going to be reliable, that it can actually figure out when it runs. So, for example, if you call a method on a variable of a given type, it will check that that method exists, it will resolve overload, it will do overload resolution, it will basically sanity check everything that you're doing. This is great when the compiler's got as much information as you have, but that's not always the case. Take the example of COM_interop. So I'll get rid of that just for a moment. A lot of COM libraries, particularly old COM libraries, and I'm looking at you, Microsoft Office 2010, a lot of COM libraries return quite weak typed information. So, for example, this is an application that uses the Excel type library. Now, the Excel application object has got an active sheet property that represents the worksheet that's currently active in Excel. What type do we think that is? What type would it be useful to be?
Object.
Anyone going for worksheet? That would be useful? Do you think it's a worksheet? No. It's an object. Because for some reason they couldn't figure out that it was a worksheet. In fact, in the .NET 4 version of the type library, they've actually now updated it so that the return value is actually typed as dynamic rather than just as object. But in practice, that still means you can't really do anything with it. You haven't got any IntelliSense or anything like that. But it does mean that although the compiler doesn't know that it's really a worksheet object, you do know that it's a worksheet object because you're smart and you've read the Excel documentation. You have read the Excel documentation. Okay, we're doing well. So, for example, you know that the result of ActiveSheet is going to have a name property. It's going to have a cells method. It's going to have a range method. The compiler doesn't know that. So if I were to write this as object, which is all that we're actually getting from the type system, you can see the compiler is not going to let me write my program. It's going to say, I can't prove to myself that those methods are going to exist. So I'm not going to let you even write the program. But because I know better, I'm going to say, compiler, get out of my way. I'm going to do this thing. I talk that to my compilers all the time. And that means that when I run it, needless to say, I've guessed correctly, Excel works, everything is happy, I get results out of it. Of course, there is a downside to this, which is that when I, for example, get my spelling wrong, terrible things happen. I get the exception at runtime rather than compile time. Because I've told the compiler I know better, the onus is now on me to get things right. So what's actually happening with what does the dynamic keyword actually do? Well, it can do a number of things. The dynamic keyword basically defers lookup until runtime. So what happens at runtime? Well, at runtime, something called the binder, the runtime binder, the C# runtime binder runs to try to resolve whatever method or property you've told it is going to exist. And there's three basic cases that it knows about. Firstly, if it sees that you've got a plain old CLR object, it will use reflection, good old reflection, try to find the property or method, try to find the right overload, and call that property or method. Life's good. If you've got a COM object, it will use the COM dynamic query system, the COM dynamic name dispatch system, which is called iDispatch. For those of you who remember the good old days, it will use the iDispatch interface to try to map whatever method name or method or property name you've given it to a COM virtual table entry, and it will then call that entry. It will use a DISP interface, or it will use iDispatch. The final option, which is kind of new with .NET 4, is it will use something called the dynamic language runtime. What that means is it will look for a particular interface, which we'll talk about a little bit later. And if it sees that interface on an object, if it sees that the thing that it's being asked to perform an operation on implements that interface, it will not use reflection. Instead, it will call that interface and say, you, object, you think you know so much, dispatch this. Because compilers talk like that as well. So this allows a bunch of scenarios. So we've seen that this makes some COM interrupt scenarios a little bit easier. It allows you to do some really kind of weird things with .NET objects if you really want to. It allows interoperation with dynamic languages like Ruby and Python. So for example, with a Ruby or Python class, the class is not compiled into a DLL. It doesn't have static type information that the compiler can consume. Instead, some script runs at runtime, and that will create classes and methods at runtime. Therefore, that resolution has got to be deferred until runtime. So dynamic is really important when you're interoperating with dynamic languages. But dynamic also enables some intriguing scenarios just within C#. In the cases that we've talked about so far, what we've got is the case where we're calling a property or method because we know that it exists. We know that COM object has got that method. We know that we're going to run a Ruby script that creates that method, whatever. But dynamic also allows you to call methods and properties that don't exist. Does that sound really useful? Of course it's useful. I wouldn't be mentioning it if it wasn't. So let's take a look at ASP.NET MVC. So how many people here have used MVC3, ASP.NET MVC3? Quite a good number. Excellent. Okay. ASP.NET MVC splits responsibility for display. I'm going to be really crude about this. It divides the responsibility for displaying a web page into, I guess, two major components called the controller and the view. The view is basically the HTML page, which can contain a little bit of script like this, and the controller is the thing that contains the actual logic for populating that page. Now, obviously, when you're writing a controller, when you're writing some logic that sort of calculates, for example, the values or goes and fetches the entities, you need to communicate what the controller wants displayed. It needs to be able to tell the view, these are the things that I want, that you need to know in order to render. Now, one obvious way to do that is to create a little object with the necessary properties and send that over to the view somehow. The problem is you may have a very large number of controllers and views in your application. If you're going to create a little object for each one of them, it would get very tedious. So in this example, my home page is just displaying a message and it's displaying a curse, as you do. Other pages might be displaying things like greetings and titles. And if we wanted to have a little class for each of those, it would get quite boring to write. So what ASP.NET MVC does instead is it allows the controller and the view to basically share an object called the view bag. Now you can see the view bag has got message and curse properties, and similarly it's also got greeting and title properties. Microsoft's shown a great deal of forethought in that any property that I can think of that I want to send to my view, I can have on the view bag. So how does that work? Well, view bag is of type dynamic. And that means that when I set a property on the view bag, the compiler does not check whether that property exists or not. It just says, I'll leave it to runtime and hope the property is going to exist. But viewBag, rather ingeniously, derives from this dynamic object property we talked about. So if we just run this up, which will show you that it's all actually working. So when that page displays, let's get rid of Excel. When that page displays, there we go. You can see that that message has come across. So we put a value into the message property. We got it out again in the view. We put a string into the curse property in the controller. We got it out again in the view, and those are both showing as you would like. Now, the other thing I printed in the view is the type of viewBag, which is this MVC Dynamic View Data Dictionary, and this is where the magic begins to happen. Dynamic View Data Dictionary derives from a class called Dynamic Object. Dynamic Object implements this interface, iDynamic Meta Object Provider, which is that kind of signal to the runtime binder of, I'm a dynamic, I can do crazy things with properties and methods. Don't call reflection, call my interface instead, and I'll sort you out. The way that Dynamic Object is implemented is that it's got a bunch of virtual methods, try do this, try do that, try do the other, which handle any unrecognized property or method calls. So when the dynamic binding takes place, when that dynamic call is made, it ends up going into one of these try get, try set, try invoke kind of members. So if we go back to our dynamic view data dictionary, you'll see it overrides try get member and try set member, because those are the two methods of dynamic object that implement getting and setting properties. So when you write in your C#, I want to set the message property, that eventually winds up to being a call to try set member. When you try to get the message property in your C#, again, because of the dynamic dispatch, because of the runtime dispatch, that ends up being a call to try get member. If we look at the implementations of these things, they're pretty much what you'd expect from something with the word dictionary in the name. It looks at this binder object which contains the method call information. So it gets the name of the property that you're trying to set, and it gets the value that you're trying to set it to, and it just stashes that in a dictionary. When you do a get member, correspondingly, it just gets that, it looks up the name of the property you're trying to get and gets that out of the dictionary. So the runtime binder is kind of converting the method call or the property call into a string, a name, and sending that down to this try get member or try set member method. Is it pretty clear what's going on so far? Is that all making sense to people? Okay, this is excellent. If we'd done this earlier in the week, you'd be way ahead of me by now. This is awesome. Okay, so let's just close down that thing. Having a few mouse problems here, so do be patient. Okay, so one of the nice things about Dynamic Object is if we look at that, that's a public class. That's not some secret internal class that only the framework is allowed to use. That's a public class. And what does it being a public class mean? It means we can derive from it and do crazy stuff. This is going to be good. So, let's just get rid of some of these things. So, what I'd like to do, just as an example of this, is I'm going to create a dynamic repository. So this is like if you use an object relational mapper like Link to SQL, Entity Framework, Lightspeed, NHibernate, something like that. You'll be familiar with the idea that you've kind of got a repository object which exposes methods on it that the application code can call those methods. And it will get collections of objects back. The method implementation will go off to the database, fetch some records from the database, materialize those into objects, so you don't have to do all that tedious mapping from ADO.NET data readers into objects yourself. Don't get too hung up on the object relational mapper side of things. I'm just using that as kind of a motivational example. So what I'd like the users of my repository class to be able to do is to write methods like this. Find penguins by species, find penguins by species and name. So essentially to write queries in their method names. Now, there's one problem here. I can't actually implement methods called find penguins and find penguins by species and so on in my repository class, because my repository class is going to be general purpose. And it's not going to know about your particular entities. If you're working with, you're doing a zoo application, I don't know about your zoo entities. All I know is the internals of my repository, about how to access databases, how to materialize things. I don't know about your concrete types. So I can't implement this method. What I can do is I can make my repository a dynamic object so that when you make up your own methods, if they adhere to a scheme, a sort of shape that I recognize, then I can pick that apart and I can actually execute code in response to that. Now, this is not a general open contract of you can write any method you want, any method name you want against my repository, and I will do something sensible. You've still got to adhere to my naming conventions. So even though it's kind of an informal contract, there's still a contract there. But rather than laying down, this is the API, these are the 5 methods that I will support, what I'm saying to you is these are the 5 kinds of method that I will support, and any actual method that you want to use that conforms to one of these kinds of methods, I will support that, even though I don't recognize the method name itself. How does that work? Well, let's kick off. Let's look in Dynamic Repository 1. So this is our first version of the implementation. And you'll see, as I said, we inherit from dynamic object. That's what hooks us into this ability to intercept these method calls. We then need to override the appropriate member of dynamic object for method calls, and that one is called try-invoke-member. Now, when the runtime binder calls try-invoke-member, it'll pass us 2 things. Firstly, it'll pass us this binder object, and that binder object is kind of a fancy name for it's the method name and other information about the method call. The other thing it will pass us, obviously enough, is the list of arguments, the collection of arguments that were passed, the argument values that came into the method call. In return for that, we've got to give it 2 things back. We've got to return a Boolean saying, were we able to handle this method or not? Did I recognize the method? Did I process it? If I did, then I've also got to populate a result saying, this is the result of the method call. This is the return value of the method call. So how shall I implement try-invoke-member in order to fulfill the kind of contract that we saw in these unit tests? Excellent. The first thing I need to do is check, does the method start with the word find? I only recognize find methods in this example. So I'll look at the binder.name. Does it start with find? If so, I'm happy. I'm going to go and do some actual work. If not, I'll just hand off to the base class implementation, which will probably throw an exception. But you broke the contract. It's no longer my problem. If I do recognize the name, if it does look like it's a find method, then firstly I'll just get rid of that find at the beginning because that was just introductory stuff. And then I need to actually look at the rest of the string, the rest of that method name, and build a query out of it. And at this point, the dirty secret of dynamic programming is that from this point on, it's all just string diddling. Diddling is a technical term. From this point on, it's all just mucking around with strings, breaking strings apart, and trying to put together an appropriate behavior given the strings. Dynamic programming is a fancy way of passing strings into a method. I feel I'm adding so much value here. So let's talk about how we actually make a query. Well, we've got the query text. First thing we need to do is, we saw it was something like find penguins by name. So the first thing we need to do is pull out the name of the kind of entity. So we'll look for anything between a find and a by. That's the filter separator. We then need to resolve that to being a type of entity, which you might do by, for example, using a singularization library like Inflector.net that knows how to make singular names and doing a type lookup, or as I'm doing here, cheating, which I thoroughly recommend as a development technique. We then construct a query this is kind of Lightspeed specific. You would do something a little bit different in Link to SQL or in Hibernate, but hopefully it's going to make sense. We create a query object, which is kind of like a SQL statement. And then what we're going to do is we're going to split apart all of those ANDed together clauses. That's what this multiple filter separator does. We'll split them apart, then we'll just iterate over them, and we're going to basically build up a filter, a where clause, effectively, from looping around the attribute names and the argument values that correspond to them. It's probably easiest to see once we fire this up in the debugger and take a look at how it works. So let's start with the most complicated one, because that's always easiest. So we come in here, we've got our invoke member binder, we've got some arguments. If we have a look at those arguments, they're what you'd expect. Those are the arguments that you saw being passed into that made-up method. We can look at the binder.name, and again, it's what you'd expect. That's the name of the method that my caller, my invoker, made up. It does conform to my scheme, so I'm happy. And I'm going to make a query as a result of that. If I just skip over that, it's all just string parsing. So I'm able to look up my entity type, and that's an entity type that I've defined elsewhere in my program. It could be something that you've constructed. Well, clearly, in reality, of course, it would be something that you've constructed in your own programs. I've put all this into one library. Don't worry about it. But I've got a type. I'm going to build a query for that, and now I'm going to start looking around the rest of the name, the rest of the method name for the attributes, so I can match them up to arguments. So I've got two things in my filter attributes array. I've got species and name, as you'd expect. The first one is species, second one is name, and those will match up, as you can see, with the arguments that were passed in. So you're having to pass in the arguments in the same order as you put the names in the query string. You can see I'm just iterating around that. And that entity.attribute, that filter and equals entity.attribute stuff, that's just building up. It's like building up a where clause in SQL or building up a where expression in Link to SQL. Again, it's maybe a little bit unfamiliar syntax. Don't worry about it too much. Is it clear how that expression is building up, that and building up over time? Mostly nodding, that's good. So once we've finished looping around that, just to clarify that to you, if I look at that query expression, you see it's built up into the sort of query you might expect. You can imagine that as being like a SQL statement, yeah? Can you see how that statement came into being? Okay. So, and after that, it all stops being exciting, because now we just do effectively a database query, and we get a result out, and hopefully it's the result we want, but it's probably more likely a database error. No, excellent. Okay, so we actually get back the one thing in this case that matches. And if I just run that outside the debugger, yeah, oh, there we go. So you can actually see that some SQL, this is coming out of Lightspeed, it's, again, like Link to SQL or in Hibernate criteria. It's generated some SQL for us, and you can see, most importantly, that SQL does respect the inputs, that method that did not exist. It's been executed, mapped to SQL, run on the database, and we've got correct results back. Are people pretty comfortable with that flow of, from that, we've made up a method, it's been passed into sort of a little interpreter, that's been translated down to SQL, and we've got results back out of it? Does that make sense, how that flow has gone? Okay, in that case, it's obviously not complicated enough. Let's make it more powerful. You may have noticed there's two unpleasant problems with my API so far. Firstly, it doesn't support anything other than equality. So I can only do equality matches. That's a bit of a limitation for a database query, you may think. Now, obviously, I could fix that by adding some sort of naming convention into my method names, into the kind of method names that I support. But at that point, if I do that, you're going to end up, that brings us to the second problem, because you're going to end up then with method names like find penguins by age less than and species starts with, which is not my idea of a good time. Because the compiler does not check the method names that you're using, having a really long, complicated method name is a recipe for disaster, because the chances of anyone typing a long and complicated method name correctly are 0. absolutely 0. So it would be nice if we could kind of break this thing up, break our API schema up into smaller, more manageable bits where it would be easier to spot what's going on. Unfortunately, another C#4 feature allows us to do that. So here's another version of my API where I'm only going to have one method, which is the find penguins method. But I'm going to allow it to take arguments. Oh, please don't do that. I'm going to allow it to take arguments. And what's more important, I'm going to say, you guys, you users of my repository class, you have to name your arguments. So instead of putting the name into the method name, I'm going to say, name the arguments. Now, there is a now, this also means that we can perform a neat little trick of saying, let's allow people to put a wart on the argument so as to specify a comparison other than equality. So this actually reads reasonably nicely now. Find penguins, age less than 9, and I can also allow other named arguments like this order by argument. If you look further down, you'll see I've also supported limit and offset for sort of paging scenarios. I'm using these as, again, named arguments that just translate into different bits of SQL. So how do we implement that? Well, it's pretty similar to the previous one, but there's a few little additional bits that we need to know about. So again, we inherit from dynamic object. We're still dealing with methods, so we're still on try invoke member. We're still doing the same kind of checking, but the first thing we want to do is make sure that all of our arguments are named. If you pass me an unnamed argument in this version of the API schema, then I'd have no idea what to do with it. Therefore, I'm going to insist that all arguments are named. So I'm going to look in this call info, which contains a bit more extra info about the invocation, and say, how many arguments are there, and how many names did you give me? And if those match up, then I'm happy, and if they don't match up, I'm going to give you the exception you deserve. If they do match up, then obviously I'll carry on, trundle on into my make query, and this largely works in the same kind of a way, but there's a bit less string parsing involved. Instead, all we're going to do is iterate over these two arrays, the argument names and argument values collections, iterating over them in parallel, and for each entry, because they're the same length, I can do that safely. For each pair in that pair of arrays, I'm going to update my query. What am I going to update it with? Well, if it's a simple name, simple argument name, then I'll add an equality comparison. If I've got an underscore in there, then I'll split it into the attribute name and the comparison operation, and I'll build up another little fragment of SQL in that. So here's my getQuery filter from an attribute name and a comparison name and a value. You can see it's kind of, again, if you were doing link to SQL or NHibernate criteria, you'd write this slightly differently, but hopefully it's pretty clear what's going on there. I'm building up expressions like link expressions bit by bit, depending on the names that I'm seeing in the incoming named arguments. Sorry, in the incoming argument name. Again, it's probably helpful if we just quickly run through that in the debugger. So if we dive into there, then we can see our list of argument names is that age less than and order by. Our argument values are 9 and name. That's pretty much what we'd be hoping for given what we've seen. And if we just tootle on down through here, then our first call to update query, we're going to get an argument name of age less than an argument value of 9, which means that we've got two components, and what are we going to build in response to that? So this is the age less than 9 bit of the age less than 9 argument. So you can now see that string parser has split it into age less than 9, and that switch statement builds the appropriate little bit of expression, and that gets added to the query as a whole, and we'll then just keep going around that loop. That will also bring in the order by eventually, but I don't want to speak to that right now. So again, if I run that, chunk, and we have a look at the generated SQL, then you can see that where clause has come in correctly, and essentially you can also see that the order by has come in correctly. So we've broken away from requiring these sort of monolithic method names. We've split it up into these smaller chunks. We've got a method name that tells us the type. Then we've got these arguments that tell us what the comparisons are and any other features that the user wants applied to the query. And bear in mind, I've not had to implement these find methods. I've just implemented a generic kind of scheme for APIs, and now you can write any methods that you want, any method names that conform to that API, to that scheme, and they become part of your API, they become part of your language. Is it clear, once again, is it clear what's going on there? Is everyone able to follow through what's happening there? Slightly fewer nods that time. Okay, let's see how this goes. All right. I want to give another example of this, which comes from the world of WPF data binding. How many people here have used WPF or Silverlight? Silverlight, pretty good number. So you'd be reasonably familiar with data binding. So Ian Randall, who is, I would say, one of New Zealand's leading experts on WPF and XAML, he got very bored of writing view models. Now, view models are really handy in WPF because they're the things that you bind to, but if you've kind of got, if they're not really doing much, if all they're doing is just sort of surfacing a little bit of data, then actually writing out the view models, writing out all those property change notifications becomes very tedious. If you're, say, for example, getting an XML document or a JSON JavaScript object notation document from a web service, then it would be kind of nice if you could just create a class with all the appropriate properties without having to write it out by hand. So that's what Ian did. So I'll just switch over to his demo. So Ian created a class called notifying dynamic object, and again, derived from dynamic object and implementing iNotify property changed, which is the key interface for WPF data binding. Because he's dealing in properties, he's overriding try get member and try set member. So we can see there, try get member, try set member. And like that ASP.NET view data dictionary that we saw, he's basically just storing things in a dictionary. So he's got this private dictionary member up here, and when he does a set, then he assigns, and then he updates that dictionary. But also he raises the property changed event so that WPF will know that the value has changed. The other thing that he does is he's got a little utility method to create one of these things from a JSON document that you might get from a web service. And I don't have time to talk through this in detail. If you want to know more about this stuff, Ian is doing a talk at Code Camp, which is on Sunday at the Auckland University Business School, I think it is. Ian will be doing a short talk on the dynamic view model stuff. It should be really good. There's lots of other great speakers. Do go along. So Ian has got this try-parse method, which uses a JSON parsing library from another New Zealander, James Newton King, JSON.net it's called, and basically takes in a string that might come from a web service and runs over that. Let's see if I can find it. There we go. And parses that into one of his notifying dynamic objects. And what he's doing is basically iterating over the key value pairs in the JSON. You can think of these as being a little bit like XML attributes and elements. So he's iterating over all the elements in this JSON document, and he's just basically setting a property. So he's on the dynamic object, he's creating a property whose name is the name in the JSON document and whose value is the value in the JSON document. There's some extra stuff in there about dealing with sub-objects. So a JSON document can have properties can be sub-objects or arrays. Again, he's got some code in there to handle that. And I've forgotten to plug in my network cable, so I will just do that now and hope that the computer will be happy with me. So if you're familiar with the Stack Overflow Q&A site, Stack Overflow it's got an API, a web service API, so you can send it requests and it will send you back JSON documents containing answers or information about users or all sorts of other fascinating pieces of information. So Ian has written this little sample application where he is querying that. He's basically pulling back a user's, he's doing a user's request to Stack Overflow. That's returning to him a JSON document. There's a lot of asynchronous nonsense going on, which we're not very interested in. But he's basically taking that JSON document and creating a dynamic object from it. And that create, as part of that create, that's creating all the properties from that JSON. That's creating a bunch of properties on a dynamic object from that JSON document. And what Ian is interested in for his display is the user's property. Now, the compiler doesn't know that this dynamic object has got a user's property, but Ian does because he's read the Stack Overflow documentation. I guess they have documentation. You never can tell with these people. Ian presumably has read the Stack Overflow documentation and knows that they have a user's element in their JSON, which he knows will translate into a user's property on his dynamic object, which will contain an array of something. He knows what properties there are in there because, again, he's looked at the JSON schema. He'll know what properties one of these user things, one of these sub-objects has got. So now, in his window, he can data bind to those properties. And somewhere in here, where have we got? There we go. So he can now data bind to those names that are coming from the JSON document. He's not had to write a user object himself. He's able to effectively data bind to values in the JSON string, in the JSON document that comes back from Stack Overflow, without having to write a class to capture those things. So now, when I look Ian up on Stack Overflow, there's the man himself at the top, as he belongs. Okay, so that's a really quick run through. Like I say, if you want to know more about that, if you're interested in using dynamic in a WPF or Silverlight context, Ian's talk on Sunday will be well worth going to have a look at, and I'll put the link up at the end if you want to pick it apart for yourself. Okay, what else do we want to see? So, I've said that this sort of dynamic programming thing is kind of glorified strings. I've kind of basically defined my methods in my dynamic repository in such a way that it's kind of, you're sending me a string, and I'm actually just doing some processing on that string. But actually .NET includes quite some interesting capabilities for runtime code generation. So actually building new code at runtime. And some of those are useful in a dynamic context, some of them are useful in a static context. I'm just going to show you a couple of those techniques right now. So let's continue with the object relational mapping theme. If you're building an object relational mapper, or even a simple internal data mapper, you're not using a full-on ORM, but you're still doing some data mapping. If you've got a lot of records coming back from the database, you're materializing a lot of objects. Now, if you're building a library, a repository, or an ORM, something like that, that has to materialize arbitrary kinds of objects. So one of your users is going to define an entity type, and you have to create instances of that entity type. You can't write new dromedary or whatever, because when you write your library, you write your ORM, you don't know about the dromedary type. That's going to be built by somebody else a year down the line and on the other side of the world. So you've got to find some other way of instantiating a type that you only get to find out about at runtime. Now, the good news is that the .NET Framework, since version 1.0, has included a method to do exactly this, called activator.createInstance. You give it a type object, it creates an instance of that type, and everybody is happy. Except that activator.instance is very, very slow. It's part of reflection. All reflection stuff tends to be pretty slow. Activator.createInstance incurs that overhead. What would be really cool, what would be really more efficient, is if we could somehow write code, if we could have code executing that actually went new dromedary, new your kind of entity, because that is a lot faster than using reflection. But how can we write that when we don't know about those types until runtime? Well, the answer is we write code at runtime and we compile it at runtime. And that way we've got a strong type method that hits the constructor directly without having to go through reflection. And we can execute that through a delegate. And with .NET 3.5 expression trees, it actually becomes, I was going to say really easy, I'll moderate that to fairly easy, to write one of these things. It's actually really easy, it's just a bit scary. So what we kind of want to do is we'd like to create a delegate. We'd like to create a delegate that did that. So if we could write a method that did what that lambda does, where t is the type we're given at runtime, that would be the same as calling the constructor. That would be really blindingly fast, yeah? But the problem is we don't know what t is at compile time. But what we can do is we can use 3.5 expressions to build up something that represents that lambda, an expression that represents that lambda, is equivalent to that lambda, and then compile that to a delegate. So how would I express new whatever in an expression? Well, it's really easy. Expression.new of whatever type I want the expression to create. That just represents, that's not doing anything, it's just a representation of a call to the new, a call to the constructor. Same with this. So expression.lambda creates a representation of a function. And that expression.lambda of func of objects is the expression of a function that takes no arguments and returns some kind of object. So if I kind of represent that as, woo, typing problems. That's what expression of func of object means. But I'm passing in the body of my lambda expression is going to be that make new. So now I'm effectively taking that and I'm pasting that in as the body of my lambda. And now I can compile that lambda, which turns it from an expression tree, a description of code, it turns it from a description of code into actual executable code. Just like the C# compiler turns text into executable code, expression.compile turns this abstract tree into executable code. Oh, sorry, what? I'm sorry? Is it fast? I'm glad you asked that question. That's an excellent question. Let's see how fast it is. So here I'm going to do 1,000,000 creates, and I'm going to do 1,000,000 with activation.create instance, and I'm going to do 1,000,000 with that compiled lambda expression. And let's see how they match up. Yeah, I'd say that's fast. I'd say that's about 7 times faster. No, it's 5 times faster. Sorry, my mistake. It's only 5 times faster. And so you can do that with any kind of reflection-based code. If you've got reflection-based code at the moment, you can turn it into expression trees. You can compile those expression trees, and you'll get out something that is much, much faster. Instead of running in a kind of interpreted behavior where every time it's got to go and look up that method, look up that property, do a reflection call, you can actually build that code structure once, compile it down, and call it repeatedly. And it'll be as though you were executing a native method, even though, a compiled method, even though that method was compiled at runtime when you knew what you were dealing with, rather than at compile time the way it normally is. Does that make sense? Awesome. Okay. So another example of creating stuff at runtime is the ability to create classes at runtime. You know, I think, well, that's pretty weird. I mean, if I create a class at runtime, how do I know what to do with it? I don't know what properties it's got, I don't know what methods it's got. How do I actually call that stuff? Obviously, you could call it using dynamic, but another way you can do this is you can say, I want a class that implements a certain interface. So if I've got an interface, ignore the scary code. If I've got an interface like that, I can create a class at runtime that implements that interface, and then I can address it through that interface. So my interactions with the class will still be strongly typed, even though the class itself didn't exist at compile time. An example of this is, once again, implementing iNotify property changed. So if you had to write a WPF or Silverlight view model, you've probably written a lot of boilerplate code where you keep, in every property setter, you have to directly or indirectly raise the property changed event. This is very boring and very hard to maintain. For example, if you change the name of a property, if you embed the name of the property into your raising of the change event, because the naming needs to be in there. If you embed that as a string, then you have a maintenance nightmare. There are tricks you can do with expression trees to get around that, but they're also a little bit on the fiddly side, and they involve a lot of boilerplate code. There's no way of getting away from that. If, on the other hand, I didn't write that class at all, but just wrote the interface, and then got C# to generate me a class at runtime, then I wouldn't need to write that stuff. I would just write the interface, and magic would happen to make it bindable, to make real bindable classes. How do we do that? Well, there's a feature called dynamic assemblies, where you've got these rather terrifying things called assembly builders and module builders and type builders and all of that kind of stuff. And the basic idea is that you can create your own types, you can create fields, you can create methods, you can create properties, all at runtime. The downside is that at some point you have to implement those methods. And implementing those methods is scary because you have to write IL. I'm not going to walk this through in too much detail, but basically what it comes down to is I'm going to, for each property in the interface that I want to create an implementation for, I'm going to create a backing field, I'm going to create a property, and that property needs a getter and a setter, and I'm going to implement the getter and the setter. And as you can see, implementing the getter and the setter actually looks pretty unpleasant. I'm sorry? Why don't you use the C# compiler? That's an excellent idea. The reason is because the C# compiler is very heavyweight. So if I'm doing a lot of these classes, potentially a bit of an overhead in terms of actually running the C# compiler. It is certainly a viable option. So there's a couple of ways to do it. You could, for example, emit the code as text and run the C# compiler from the code DOM, or you can also use code DOM to emit abstract trees, which are kind of like expression trees but old school, and you can then compile those. So that's certainly an option, but the C# compiler is very heavyweight. It takes a long time to invoke. Now, in a lot of environments, that's not a concern, so it's a really good technique to be aware of. So thanks for raising that. But where you want to have something that's a little bit more lightweight, then these dynamic methods, these dynamic typed, IL generators, are actually a little bit more handy. But they are a lot more scary. If you're more comfortable with C#, and who is not more comfortable with C#, then you may want to go with, sorry, did I catch your name? You may want to go with Wilfred's suggestion. But fortunately, this IL stuff doesn't need to be as scary as you might think it is. So the way that I always write these things, if I do have to write these things, is I steal the code. So I write something like public class example, and I basically implement a minimal version. Oops. I implement a sort of minimal example of the thing that I want to generate. Now, I compile that, and I load that up into ILDASM, which is like a freaky version of Reflector. This actually shows me the underlying IL code. So if I look at that class, I can see that property, for example, and I can see those method implementations. And frankly, those method implementations look kind of scary as well. And you might think that two scary things is worse than one scary thing. But actually, this is really good, because now I don't need to understand that at all. All I need to do is copy that into my source code. So I don't need to understand what's going on. Well, and it helps, obviously. But basically, if you look at what I've done to implement my dynamic code generation, let's compare, for example, this creation of the set method against what you can see from disassembling my representative example. You can see there's a one-to-one match between those lines. Now, obviously, I'm using variables instead of literal names in my code because I've got to vary things. But what you can see is that I've basically copied those opcodes from ILDASM into my IL generator, and a monkey could do that. Yeah? So I know that what you're actually seeing there is a little bit obscure, but it's actually not as scary as you might think. I'm not, by the way, encouraging you to write code that you don't understand. That's what the entity framework generator is for. Okay. Can't say things like that. Okay, we're running a little bit low on... What? Sorry? I actually have to, it's part of my job. Okay, what else do we want to have a look at? I want to briefly talk about that dynamic meta object provider. So we've been kind of coasting by using dynamic object all along. Dynamic object is really handy, but it kind of hides us from what's really happening. And sometimes it's not an option. Suppose that I've got something like a link to SQL data context or a Lightspeed unit of work, and I want to offer you a dynamic API on that. The problem is I can't now derive from dynamic object because the data context already derives from, well, it's defined in the framework. It's a data context. I have to derive mine from data context. If I'm in Lightspeed, I have to derive from unit of work. So I can't now derive from dynamic object. But what I can do is I can implement this dynamic meta object provider interface. And that has only got one method in, which is nice because it's a pretty intimidating looking method. It's got one method with one parameter, one return value, and I don't understand what any of them are. So a meta object is basically it kind of wraps an object, but it's also got information about it's also capable of running code on behalf of that object. It's capable of extending that object. It kind of represents a dynamic class for that object. Now, in this case, what I'm going to do is implement that. I'm going to create my own dynamic meta object that represents the capabilities, the dynamic capabilities of my extended unit of work thingy. So, unit of work, that wildlife unit of work has still got all of its ordinary methods, but that dynamic meta object that I'm going to provide for it is going to give it some additional dynamic capabilities. So I return this dynamic repository 3 meta object, and I'm just deriving from the dynamic meta object. And guess what? Dynamic meta object has got a whole bunch of virtual functions on it. And those should look awfully familiar from dynamic object. They're basically the same set of methods, except that they're called bind instead of try, and they all return and take dynamic meta objects rather than returning booleans and taking objects. So that's just a lower level version of the dynamic object API. Well, that's great because we already know how to program the dynamic object API. All we need to do is override the invoke member, which in this case is called bind invoke member rather than try invoke member, but it's doing the same job. That's what's going to get called for methods. And now I just do the same logic. All of this is exactly the same as what I was doing before, with the slight change that because those arguments are given to me as meta objects rather than objects, I just need to pull out their values. And because I've got to return a meta object, I just need to do some expression-y incantations just to wrap up my result in a meta object instead of returning it directly through the result parameter. But everything else is exactly the same. All we're doing is instead of having that logic inside our unit of work class, instead of having it inside our dynamic repository class, we're shunting it onto a sort of sister, a buddy object, and hosting that dynamic logic there. And in fact, a common pattern is that you'll basically just bounce that straight back to your main object, so you can keep it all within the one object. The object can contain its own internal dynamic logic. The dynamic meta object just acts as a kind of a tennis racket that just bounces any method calls straight back to the place where they belong. Does that make sense to people? We're getting into some fairly abstract territory here, so it may take a while to settle in, but basically all we're doing is we're moving that dynamic capability out of the dynamic object clause. We're taking that dynamic capability, instead of handling it through overrides of dynamic object, we're moving it to a sister object that we can serve up through an interface. But the actual logic, how we execute it, is almost exactly the same. The only worry is that scary name, dynamic meta object, which we've seen we can pretty much get rid of that pretty easily. Just call .value, it'll go away. Okay, we're running very long time, so I'm just going to briefly talk about how C# Dynamic actually works internally. I don't think we'll have time to look at any further examples, but I'll just briefly show you some of what's going on inside. So I'll just make this the simplest program in the whole world ever, and we'll give that some build. There we go, and we'll load that up in Reflector. So what I'm going to show you now is what actually gets compiled for those innocent-looking 2 lines of code. What actually comes out in the IL. Does that strike fear into your heart? You can say yes, because it strikes fear into mine. What the dynamic binder is doing is actually, it actually looks quite intimidating. You can see that, in fact, this is actually representing just one line. There's our first line. You can see that make county thing. That dynamic keyword has gone away, and in the IL, it's just represented as the object type. That second line, however, has turned into some hideous morass of angle brackets and generated names and members and call sites of actions of call sites of types of objects and goodness knows what else. So what's happening is that whenever the C# compiler sees a case where it's got to do something dynamic, it emits one of these, it basically records that as a call site. Now in that innocent looking console.write line, there are actually 2 dynamic call sites. There's the site where we call thing.count, and that's dynamic because thing is dynamic. And then there's the console.write line, which you may think doesn't look very dynamic, but the problem is, because the compiler doesn't know what the count property is, it doesn't know what that is at compile time, because that's dynamic, that means that console.write line has to be dynamic as well, because it's got to process something that it doesn't know about until runtime. It doesn't know what overload to resolve it to until runtime. So we've got 2 call sites there, one to count and one to write line. And if we have a look in here, you'll see it's created kind of a private member variable, private class, which contains these weird call site thingies, and that's where it's going to store them. And then as it executes, it goes, have I already built this call site? Call sites are expensive enough that it's worth caching them. So that's why it's created call sites and why it's remembering them. So every time it executes, it's going to say, have I got this? Have I got the call site for, what's this one? This one is the write line call. Have I got that? If I haven't, I'm going to create a new one. And because it's a method invocation, I'm going to create it using an invoke member binder. An invoke member binder. Where have we seen one of those before? Well, that's pretty much what's going to get passed to iDynamic Meta Object Provider or try-get member or try-invoke member or whatever. So you can see here is where the process begins of wrapping up the call information in something that can be thrown over the wall to a dynamic object, as well as being processed by a COM binder or a reflection binder. So we've got one site here that's being created for the write line, and similarly it checks whether site 2 has already been prepared, and if it hasn't, it's going to create one with a get member binder, that's a property accessor, for a count property. Once it's got those call sites in place, and this is where it starts to get fun to read, is it's going to call site 1, and that's got a little delegate on it, which, actually, let's not worry about the delegate, don't worry about it. Basically, it's going to call site 1, passing in some rubbish and type of console as an argument. So remember, call site 1, that's the write line invoke. That's the write line call site. So it's saying I'm going to invoke the write line call site, passing type of console because it's a static method. Then The other argument to that is going to be site 2, which is the count site. So I'm going to invoke the count site passing thing, because it was thing.count. I've got my .count concept. I'm going to apply that to thing. That's going to return me an argument. I'm going to put that into my call to write line along with the console. There's a man there who's clutching his forehead. I don't blame you. You do not need to know this stuff to use dynamic. I'm showing it to you because it kind of gives you a bit of an interesting insight into how the C# binder is actually building things up in order to invoke stuff. If we had a little bit longer, I would show you how you could actually exploit this in your own code by building your own dynamic dispatchers where they're not available. For example, dealing with the fact that in C#, if I've got, say, one of these units of work that support dynamic stuff, some of its methods should be resolvable at compile time. Others are only resolvable dynamically. If I've got a dynamic object, a dynamic reference, a variable of type dynamic, all calls on that thing go through the dynamic infrastructure, which makes them really slow. So I want to get fast calls to the things that can be resolved at compile time, but I still want access to dynamic stuff, to dynamic calls. I need to actually maintain 2 references, one strong typed and one weak typed, to the same object, and remember to call through the right one. That's pretty crazy. There are some places, there are some techniques you can use, particularly in the F# language, where you can say, I want a strong typed call or I want a weak typed call. I want a compile time call or a dynamic call, and you can choose it on a call by call basis rather than a reference by reference basis, and you can actually exploit this infrastructure to make that work. But we don't have time to go into that, we're already running over. So, I just want to quickly flip back to the slides. There we go, there's the slides. So we haven't had time to look at the F# one. There's Ian's code. I hope I've given you some kind of insight into what's going on in the dynamic world, how you can use it to create interesting new development experience, how you can use it to maybe offer APIs that would not have been possible in traditional C#. And also just to give you some sort of insight into the kind of programming experiences that are possible from that. Thank you very much for your time. Have a great time. Have a safe journey home.